Hello everybody, my name is Ditsachart Chomkhokkruad. Today I'm gonna present about the journal in manufacturing and processing topic. My selected topic is the effects of layer by layer thickness and fiber volume fraction variation on the mechanical performance of a pressure vessel. Let's get started. First of all, I will notice the nomenclature of this topic. O is hoop winding, X is helical winding, EX is elastic modulus in X direction, EY is elastic modulus in Y direction, GXY is shear modulus in XY direction, VXY is Poisson ratio in XY direction, XT is fiber tension strength, YT is magnetic tension strength, S is shear strength, and Vf is fiber volume fraction. Now we move to the first topic, an introduction. In the past few years, filament wood composite materials have been used increasingly in aerospace, automotive, and energy industries because of their high strength-to-weight ratio. The important components produced from these composite materials are pressure vessels. Pressure vessels are built by various methods using different forms of fiber and resin materials, of which filament winding method is the main process for manufacturing of a pressure vessel. And the important process parameters may be listed as winding tension, temperature, winding and holding time, fiber and magnetic material properties, and manual rotation speed. In this study, effect of layer by layer thickness and variation of fiber volume fraction due to the manufacturing processes on the mechanical performance of a filament wood pressure vessel. The example is a model case with unicorn dome openings were investigated. The effect of the thickness and fiber volume fraction on the stress distribution along the model acceleration was shown. As well, in addition, hydrostatic visualization tests were performed to verify the finite element analysis in terms of fiber direction strain on outer surface of the vessel. Next, we will go to the test topic. In experimental study, 3 pressure vessels of the same configuration were subjected to pressurization tests until birth. Fiber direction strain was measured at 20 locations using strain gauge through the pressure vessel in each test. All strain gauges were attached at the same position in each pressure vessel. The location of all strain gauges are shown in Fig 1 and Table 1. Uniaxial strain gauge with 1 mm gauge length were used. Average of 3 tests was given as the result. In each test, pressure was incrementally increased until a sudden drop on pressure occurred. A representative plot of normalized pressure versus fiber direction strain is presented in Fig 2. A linear relation between pressure and strain was observed in all tests. There was no evidence of leakage. Therefore, the maximum measured pressure was the burst pressure for all tests. This one of the pressure vessel before and after the pressurization test. Next, finite element analysis topic. The finite element analysis of the composite pressure vessel was performed using commercial finite element solver, that is Abacus. Axisymmetric model of the pressure vessel was created with 4 non-linear axisymmetric elements. Fig 4 presented the cymatic view and dimension of the pressure vessel with wiring configuration. Next, Figure 5. Figure 5 shows pressure loading, boundary condition, and mesh view that aluminum polar bosset and steel caps were pressed to both forward and aft sides. The shear pliers were used at the interface between the polar bosset and composite casting. Figure 6 Mesh convergence study. Mesh convergence study was performed to determine optimum element number. Number of elements versus maximum stress at the composite body under internal pressure load. From Figure 6, element number was chosen at 28,998, which corresponds to element size of 1 mm. Next, widening angle distribution in dome region. Figure 7 shows about the widening angle in dome region change from the helical widening angle at cylinder region up to 90 degrees at polar opening. It also changes through the thickness at every location. Therefore, the linear geometry was updated for each helical widening layer to capture the change in the widening angle through the thickness. After thickness of manufactured, pressure vessel was measured. It was noticed that layer by layer thickness did not meet the design specification in a particular section. So, design and manufactured layer by layer thickness for particular section in cylindrical part are given in Table 2. As seen from Table 2, there is an apparent difference between the design and manufactured layer thickness. Measured layer thickness are lower than the design value for both initial helical and hoop layers. However, measured layer thicknesses are very close to the design value for both large helical and hoop layers. So, two major phenomena may explain the difference between design and manufactured layer thickness. The first one is the effect winding tension. The winding tension determines the radial compaction pressure exerted by the last hoop layer. If winding tension is high, the radial compaction pressure will be high too. Therefore, the actual layer thickness will be less than the design. The second phenomenon is the effect of the viscosity of the resin material. Low viscosity resin material tends to fall under the radial compaction pressure. The fall of the resin generates lower layer thickness than desired. The pressure vessel total thickness comparison of measured and finite element model is shown in Figure 8. In addition, the variance of layer by layer thickness also indicates the different fiber volume fraction between layers. As mentioned before, change in layer thickness is a result of falling resin. Decrease in layer thickness causes the increase in fiber volume fraction with the same amount of fiber volume. Since fiber volume fraction is directly related to the thickness, each layer fiber volume fraction can be calculated using their thickness and measured fiber volume fraction for specific section. So the calculated fiber volume fraction values are given in Table 3. As mentioned before, we know that material properties of a layer depend on the fiber volume fraction of that layer. Therefore, material characterization tests must be carried out for each layer due to their different fiber volume fractions. Because of the high cost of the material characterization test for each layer, so micromechanic simulations were performed to obtain fiber volume fraction of each layer. The relationship between the fiber volume fraction and material properties were found as these four equations. And material property of the layer with 60% fiber volume fraction are given in Table 4. Now we come to the topic results and discussions. The comparison of strain gauge measurements and finite element models representing the design and manufactured pressure vessel is shown in Figure 9. Although there is quite layer by layer thickness difference between the design and manufactured pressure vessel, the analysis results of design and manufactured vessels are compatible in terms of strain distribution of outer helical layers. This result shows that the designed and manufactured pressure vessels have similar overall stiffness. Also, strain distribution of outer helical layer was well captured by analysis as shown in Figure 9. And next topic is figures. Despite of having similar overall stiffness, the designed and manufactured pressure vessels have different layer by layer state fields because of different layer by layer fiber volume fractions. Figure 10 shows us fiber dilation rate of the first helical layer for designed and manufactured pressure vessels. The manufactured pressure vessel has higher fiber dilation rate due to higher fiber volume fraction for this layer. Similar to fiber state behavior of the first helical layer, fiber state of first hoop layer for the manufactured pressure vessel is higher than the designed pressure vessel. Figure 11 shows fiber states of the first hoop layer for both designed and manufactured pressure vessels. Due to higher fiber volume fraction, the manufactured pressure vessel had higher fiber states than the designed pressure vessel in the first hoop layer. Figure 12 shows that the maximum fiber state occurs in inner hoop layer for manufactured pressure vessel. In addition, the inner helical layer has higher fiber state distribution than outer helical layer along the pressure vessel. And next, in contrast to the manufactured pressure vessel, maximum fiber state occurs in inner helical layer cylinder dome transition region for designed pressure vessel as shown in Figure 13. Also, the inner and outer helical layer have similar fiber state distribution in cylindrical region. From all figures, it can be concluded that true thickness fiber volume fraction variation may change the stress field distribution along the pressure vessel. It is so important to consider the true thickness fiber volume fraction variation for accuracy of the finite element analysis. Now we read the last topic, conclusion. The filament wood composite pressure vessel with unicorn openings was studied in order to investigate the effect of variation of fiber volume fraction through thickness on the mechanical performance. The pressure vessel was designed, manufactured, and tested while strain distribution at outer layer of the pressure vessel were modulated with the strain gauge in specific locations. Thickness and fiber volume fraction of the designed and manufactured pressure vessel were compared. So, finite element analysis were performed for both the designed and manufactured pressure vessels. The fiber dilation strength were measured along composite outer surface. An excellent agreement was achieved between the test and finite element models. The state field of different layers was compared for designed and manufactured pressure vessels. The importance of considering the true thickness fiber volume fraction variation was emphasized. Well, that's it from me. Thanks very much.